So it's our last week of class. We're continuing to focus on differential equations. There's still some things to learn. We're going to go back to the logistic model. This is the content of section 11.7 in the book. But I'm going to do a little bit extra than the book does. I'm going to add some harvesting to the model, not for the main part of what we do, but at the very end, I want to ask what happens if we allow for harvesting. In other words, for example, if the model was a population of fish, what if you allowed fishing? Such as fishing. Very appropriate subject for Minnesota here. And let's go ahead and pretend we're talking about a particular lake in Minnesota. Let's let P be the population of, let's say, walleye, a very common kind of fish in Minnesota here. Walleye, although I forget how you spell it. Is it two L's? Yeah. Walleye.
Exactly how it sounds.
Okay, there we go. Walleye, yeah. Population of walleye in a certain lake. How about Lake Mille Lacs, which in Minnesota is a fairly famous lake. It's a fairly big lake here in the middle of the state. Think about appropriate units, probably millions of walleye, right? It's a pretty big lake. And yeah, there's typically a lot of walleye in pretty big lakes in Minnesota. Probably it's in the millions. As usual, T will be time. What makes the most sense? There's lots of things you could use. You could use months. We'll do the typical thing here, say in years. Remember that we also, in the logistic model, we did talk about this briefly about 2 weeks ago, I think, week and a half to 2 weeks ago. We also have something called the carrying capacity. In the abstract, it's typically labeled with a letter L, kind of stands for limit, you might say, but it's called a carrying capacity. You might think of this intuitively as the number of walleye that the lake can hold comfortably without overcrowding. If the population is bigger than L, then it's overcrowded. Now, that doesn't mean there's fish everywhere. It just means there's not enough food for the fish that are there. And so the death rate of fish would be higher than the birth rate, and the population would tend to decline if it's bigger than the carrying capacity. Let me also add another constant. I'll call it H for harvesting. I'll call this the harvesting rate. Of course, if it is fish and harvesting is fishing, then we could call it the fishing rate. The carrying capacity's got to be the same units as the population, millions. But the harvesting rate, being a rate, would be in millions per year. Millions of fish per year. And to keep things simple, assume it's constant. Now, that doesn't happen in reality. In reality, we have fishing seasons during the summer, during the winter. The fishing cycle, the fishing rate, harvesting rate, goes up and down over time. It might be modeled by a trig function, like a sine function or something. That might be a better model, but that sounds more complicated. In mathematical modeling, it's always a balance between accuracy and complication. We want it to be accurate, but we don't want it to be so complicated that we can't handle it. So there's always this tension between simplicity and accuracy. So for the most part, we're going to think about the case where H is 0. But we will briefly think about the case where there is a positive amount of harvesting as a rate in millions of fish per year. We hypothesize here in the model, this hypothesis might be incorrect, but it does make some sense, that the relative rate of change of the population with respect to time is proportional to the difference. I'll just write it down, but then I'll explain it. 1 minus P over L. Why? Why does that make some sense? If the population is small, maybe L represents 10 million. So L is 10 in millions. And maybe the population is 100,000, which is small compared to 10 million. It would be 0.1 million. 0.1 divided by 10 is a small number, 0.01. If that population is small, then 1 minus a small number is close to 1. On the other hand, if the population is relatively large, close to L, like if L is 10 and P is 9.9, 9.9 divided by 10 is 0.99. 1 minus 0.99 is very close to 0. The relative rate of change is going to be small. By the way, relative means percent rate of change effectively. We're talking about the percent rate. Now, that makes sense also if you think about it this way. If there's really a small amount of fish, like just 20 fish or something, P is really tiny compared to L. The relative rate of growth, the percent rate of growth will be large, but the actual rate of growth might still be small. If you don't have many fish, there aren't going to be many babies. But since the population was low to start with, if there's 20 fish to start with and you've got 10 babies in the next year, that's a large relative rate of growth. That's 50% growth rate. If 20 fish grows to 30 fish. Does that make sense? So we really do want this to be the relative rate of change, not the actual rate of change. Does that clarify anything, David, or did you just had an idea about why? Okay, sorry about that. But what is the relative rate of change? It's not the derivative, because the derivative is the actual rate of change. So what is it? It's the derivative divided by the actual population. Again, think about it intuitively. If, say, at some moment in time, L is 10 and let's pretend P is 1 million. So 1 in millions. 1 divided by 10 would be 0.1. 1 minus 0.1 would be 0.9. If the population grew from 1 million to 1.1 million, its rate of change would be about 100,000 fish per year, from 1 million to 1.1 million. But dividing that by 1 million would be a 10% growth rate. 100,000, well, 0.1 million divided by 1 million is 0.1, 10%. I'm trying to emphasize that this is a relative rate of growth. It's a percent rate of change. Having a proportionality means there's a constant in proportionality that gives you equality. You could say dp dt over p is some constant times 1 minus p over L. K is a positive constant. And then you could multiply both sides by p to get your differential equation. Therefore, your differential equation is dp dt equals k times p times 1 minus p over L. There's a differential equation. At least in the form we've been writing. I mean, this is a differential equation too, but this is more in the form we've been writing them. Is it autonomous? How do you tell? Autonomous means independent of time. No t's on the right-hand side. This is autonomous. An autonomous differential equation. And when it's autonomous, that means we can and we will use the qualitative approach we talked about the last 10, 15 minutes of class on Friday. where I draw the graph of this thing as a function of the dependent variable f of p. And that graph helps me draw the slope field and solutions in the slope field. We'll do that again today. If you take diffie-q with linear, I emphasize that a lot. I'm not sure how much AUK emphasizes this in diffie-q, the plain diffie-q course. But I emphasize this kind of thing a lot with diffie-q with linear. What if we have harvesting, though? What if h is positive instead of 0? It is a harvesting rate in millions per year. The units for the derivative are millions per year. Maybe we should just subtract it if there's harvesting. If there is harvesting, we'd be subtracting a positive number, a positive constant. That's a constant. K, L, and H are all constants. P and T are the variables. Whether something's a constant or a variable is all in your imagination. It's all in how you're thinking about it. Super important, especially when you got a lot of letters. Before we take the qualitative approach, let's get a little bit more practice with separation of variables. We can separate variables here. We can get all the p's on the left and the t's on the right by dividing both sides by p and also 1 minus p over L to cancel on the right, and multiplying both sides, but pretending to multiply both sides by dt. I will take the h to be 0 to keep it simple. Again, so we'll separate variables in the case where h is 0. You actually still can separate variables even when h is positive, but to keep it simple, let's not. Here's what the left-hand side will become, and here is what the right-hand side will become. Integrate both sides. As we've always encountered, the right-hand side ends up being easy to integrate. Left-hand side's often a little harder. And that is the case here. Now, to save time, I'm going to use Mathematica to do that integral. But I would highly recommend that you do that integral by hand after class. You would have to use partial fractions, I will tell you. And your A and your B from the partial fractions would possibly depend on L. L is a constant. You don't know what it is. It could be 10, it could be 20. When you do the integral, if you leave the L as an L, the answer probably will depend on L. You should expect that. It's part of the model. It's got to be in there. Let's just get Mathematica to do the integral. When you use partial fractions, it would be A over P plus B over 1 minus P over L. You should expect to get logarithms when you integrate, as you may remember from integrating functions like this. And Mathematica can handle it with an L in there just as an L. It even colors it differently. It knows that the sort of teal colored is the variable and the blue color is the constant. There's how it gives the answer. Of course, you should add a plus C. We can also expand the L through. If you do a / expand with a capital E, it will multiply the L through. You should know, though, when you do it by hand, that you should have a plus C. And you also really, in theory, should technically have the absolute value signs around the P and the P minus L. Though you've seen, we do end up getting rid of the absolute value signs when we allow for arbitrary constants that can be positive or negative. We've seen that. Let's go ahead and initially write it with the absolute value signs. If Mathematica is right, this integral should be natural log of the absolute value of P minus natural log of the absolute value of 1 minus P over L. You could say plus C2, but I won't bother. You put the C2 on the other side anyway. Always remember what your goal is with differential equations. With solving them, you're trying to solve for the dependent variable, in this case P, in terms of the independent variable, T. So we need to get rid of those logarithms. Use a property of logs. The difference of two logs is the log of their quotient. So I get the log of this divided by that. Oh, I made a mistake here, didn't I? This should be a P minus L in there. I mean, you can write it in terms of what I wrote. You can write it in terms of 1 minus P over L. But Mathematica is simplifying it. And I can write this as the log of the quotient of the absolute value of P to P minus L. L here. I want to get rid of the logarithm. Exponentiate. E to that power will then equal e to this power. And e to that power is e to the C1 times e to the KT. I could call this C2, say. Here the e and the natural logarithm cancel because they're inverse functions. Can I get rid of the absolute value signs? Yeah, effectively, yes, you can. This is not a full justification, but it does work. If we get rid of the absolute value signs there, then we're saying maybe it's C3 times e to the KT, where you might say C3 is plus or minus C2. It's not a proof, but it's a pseudo justification. And then solve for P. It's not as hard as it looks. Multiply both sides by P minus L to cancel it over there. And you'll get a P term over here that can be subtracted from both sides. And then you can factor out a P before you finally divide. To solve for P, what are the steps? You first multiply both sides by P minus L. You'll get P equals C3P e to the KT minus LC3 or C3L e to the KT. Subtract this term from both sides to get two terms involving P on the left, and it'll factor out a P. And then divide both sides by this, and you'll have P solved for. I would like to get rid of that negative sign right there, so I am going to actually divide both sides by the opposite of this, which means in the end, I need to switch these around like that. Should I change the C3 to a C? You could. I am going to, although I'm going to do something else first. I'm going to effectively divide both the top and the bottom by C3 e to the KT. Or if you prefer, multiply by the reciprocal of C3 e to the KT. That's a pretty standard thing to do here. It does make it a little simpler looking. For one thing, the top just becomes an L. So the carrying capacity by itself is on the top. And on the bottom, these two completely cancel to leave you with a 1. And then this times this, yes, it is negative 1 over C3 e to the KT, but I'm going to write that instead as plus C e to the negative KT. C effectively here is negative 1 over C3. So this now is a general solution. Does it solve any initial value problem? Actually, not quite. So I'll put the word almost in here. It misses one solution. This differential equation has two equilibrium solutions. Does anybody see what they are? Two equilibrium solutions. I claim you can just look at that and, again, ignore the H. You can just look at that and figure them out. 0 and L, yes, P equals 0 and P equals L. Two constant functions that solve the differential equation. In both cases, the derivative is always 0 because they're constant functions. And if P is 0, always for all t, the right-hand side 0. And if P is L for all t, the right-hand side 0. If P is L, L over L is 1, 1 minus 1 is 0. I'm pretending h is 0. That's why I said ignore it. So this misses the equilibrium solution at p equals 0, actually. There's no choice of c that can make this always equal to 0 because the top's not 0. L is a positive constant. But now let me do the other thing that I've done with this kind of thing. Let me write down what I call a generic initial value problem and find what I call the unique solution of that generic initial value problem. This does solve the differential equation no matter what C is. C is arbitrary. But if I have a particular initial condition, I can figure out what C is. Generic IVP, again, in the case where h is 0, dp dt is kp times 1 minus p over L. I'm not going to bother putting the h in there. P of 0, yes, I could pick a particular number here, 5, 10, whatever. But let me allow for an arbitrary initial condition, P sub 0, or P naught if you prefer. I'm going to call the unique solution P equals phi sub P naught of T. Why do I do that? Actually, our textbook does not do this. And actually, the textbook I use for DiffyQ and linear algebra doesn't do this either, but I like to. I have some good reasons for it. Partially, it emphasizes that phi, this solution function, is a different function than the f function. They are different. They're related, but they are different. That's one reason to give the function a name. Why call it phi? Because many textbooks do. I actually have another motivation for using this notation if you take DiffyQ with linear, in that it helps bring cohesion to the entire course in ways I can't take time to explain right now. Using this notation brings cohesion to this combo course, differential equations and linear algebra. We're combining two subjects into one course. If you're going to do such a thing, you really should try to combine the subjects to some degree. And using this notation helps me do that, okay, for the course. So if you're going to take the course, it's worth getting used to now. If you're not going to take the course, well, it's still something I think it's worthwhile. If nothing else, to emphasize that, again, these functions are different. This is f of p, not a solution. It's just the right-hand side of the differential equation. That's a solution. It's a function of t. It's a little weird. Here in that function, p is the independent variable. Here in this function, p is the dependent variable. Which is it? It all depends on your perspective. For a solution of the differential equation, p is dependent. For this expression on the right-hand side, which you could think about without bothering to think about the differential equation, it's independent. It all is on how you're thinking about it. But they are related. We're about to talk about the qualitative approach too. Anyway, can I figure out how C depends on P naught? Yes, you can. I can say, use this, P naught is P of 0, which I can now write using function notation, is phi sub P naught of 0. Go up to this formula, use it. And just solve for C. Plug in T equals 0. E to the 0 is 1. I can solve this for C. Take the reciprocal of both sides. This means 1 plus C over L equals 1 over P naught. Multiply both sides by L. This means 1 plus C is L over P naught. Oh, no. Yeah, okay. Yeah, that's a 1 here. So I got confused. I thought that was an L. And that means C is L over P naught minus 1, which, if you get a common denominator of P naught, is L minus P naught over P naught. So the solution function can be written like this. Replace C with L minus P naught over P naught. That's okay, although it still misses the equilibrium solution at 0. If, however, you decide to multiply the top and the bottom of this fraction by P naught, something magical happens. All of a sudden, you get a formula that works no matter what P naught is, even if it's 0. That's amazing. Unexpected. It works though. Even if P naught is 0, this now works, and it will get the equilibrium solution at 0. That's another benefit of this approach, is now we have all solutions. What do we want to do now? Let's graph the solution. I'll get Mathematica make the slope field as well. And let's use manipulate to see what happens as, for example, K and L and P naught change. Let's first confirm the answer with dsolve value. Dsolve value. I do want you to know syntax for dsolve value on the final exam. There was that other command, just plain dsolve, but I like using dsolve value because it makes the answer look nicer. You put the differential equation and the initial condition inside a list with curly braces separated by a comma. The differential equation is P prime of t. You must use double equal signs. If you try this kind of thing on Mathematica with single equal signs, it messes stuff up. Because what happens when you use single equal signs is it stores things in memory that you don't want stored in memory. And it will cause problems with your code. The right-hand side is K times P of t. You do need to put P of t in there in Mathematica, not just a plain t, or not just a plain P. P of 0 equals, I'll type the P naught without a subscript. I'll just type P0 like that. Tab over, put a comma here, P of t, comma t. So this is saying to Mathematica, solve this differential equation right here using this initial condition, solve for the function P of t, and yes, the independent variable is t, not K or L, for example. Gave a little error saying inverse functions are being used. Well, it's not, it was more of a warning, not an error. But this effectively does work. And it is effectively the same thing as my answer. You could obtain my answer from this one by dividing the top and the bottom by e to the kt. Cancel the e to the kt there, cancel the e to the kt there. And when you divide this by e to the kt, it's the same as multiplying by e to the negative kt. That matches my multiplication by e to the negative kt right there. These are the same. All right, now let's graph this and also graph the slope field. I will go ahead and define my right-hand side function as a little f function. I'm using the subscript button on the writing assistant here. I'm about to include the constants in the formula here, the k and the p, or the k and the l, excuse me, as subscripts, but I do need to use underscores because I want to allow Mathematica to change those. That's why I have to use underscores. The p goes inside the parentheses here. This is a function of p. This is k times p times 1 minus p over L. Notice no t's in here. That's okay. The t's are only needed for the dsolve value to emphasize it's the differential equation where t is an independent variable. This is just a function of p. I can think about this function without any t's. Let me also use a subscript and type in the formula for the phi function. And you can make a phi by doing escape, ph, escape, makes a phi. The k will still be there. The L will still be there. But there's also going to be one more thing, P naught, which is I'm typing as P0. These are functions. This is a function of T. And its formula, I can just copy and paste from right here. Copy and paste. Those functions are now entered. You need the underscores to enter these functions to emphasize to what Mathematica what can change. But once you've done that, then don't use underscores anymore. I can, for example, now make a plot of the slope field. I don't know if you've noticed use vector plot before. I'm not expecting you to be able to use vector plot like I'm showing you here to make a slope field. This is something you don't have to know for the exam, but I want to do it here to show you. Oh, sometimes you have to fiddle with this to make it look nice. Let's just see how this looks when I do it like this. It may not look very nice, but let's just try it anyway. And then I'm going to plot the function itself in there as well, the phi function. Notice I am picking I'm picking the k to be 0.1 and the L to be 10. If you look at how that matches here, I'm picking the k to be 0.1 and the L to be 10. So I need a 0.1 and a 10 here as well. I also need an initial value of the population, maybe 0.1. This may not look ideal, but let's see what it looks like anyway. It's not too bad. Mathematica is making the line segments in the slope field as arrows. And also not including the axes, that can be fixed. That's okay, you can make them as arrows. Do notice the solution is following the slope field. By the way, I can make an option where they don't look like arrows. That is possible, but I won't take the time to. So there, when k is 0.1 and L is 10, is a solution. And the initial condition is 0.1 as well. So this is 100,000 fish to start with. And it's predicting that, for example, by the time you reach 40 years, the population's up to about 4 million fish. By the time you reach 80 years, you're getting pretty close to the carrying capacity of 10 million fish. Does that match reality? Probably not, right? How could you make it match reality? You might have to pick a different value of k, like maybe 0.3 instead of 0.1. Then it goes up faster. You reach close to 10 million fish by 20 years instead of 60 years, whatever it was. If I make k 0.5, it goes up even faster. You can fiddle with things to try to make it match reality. Is it possible it will never match reality? Yes, that's possible too, right? It's an oversimplification of reality. It's not likely that reality is going to match this exactly. Oh, by the way, if I'm going to make it follow the slope field, I need to change the k up here as well to make it follow the slope field. It's also interesting to think about mathematically what happens if you put this in a manipulate and allow yourself to change k and L. Manipulate will make animations, say for different Ks or different Ls, or maybe different P naughts. Don't worry about this syntax. Just trying to do something reasonable here. This allows me to make changes. So I can change the value of k, change the value of L, change the value of P naught. Changing k, yes, changes how fast everything goes up. Well, let's see. Yeah, that is working. Okay. Changing L changes the carrying capacity. What's the limit? As t goes to infinity. And changing the initial condition changes exactly that, the initial condition. Okay. What I want to show you now is that you can do all this without technology and without actually doing the solving. You can think about it qualitatively. By doing what we did last Friday. The f of p function, k times p times 1 minus p over L. Again, I'm taking the harvesting to be 0. I will briefly think about what happens when the harvesting is not 0, though. Actually, maybe we should do that right now. So I'll put a minus h here now. You can graph, this is a function of p, as an ordinary graph without thinking about differential equations at all. Since the independent variable is p, make your horizontal axis labeled with a p. What should the vertical axis be labeled with? Well, you could label it with f of p. You could also label it with dp dt, since it is ultimately related to a differential equation. I could write dp dt equals f of p up here. Weird labeling, but nothing stopping me from doing that. When h is 0, well, even when h is non-zero, this is a quadratic function of p. This is a quadratic function of p. For emphasis, you could multiply it out. The p squared term is going to be minus k over L times p squared. Do you see that? And multiply those two. And the p term is going to be plus kp, and the constant term is minus h. The graph of such a thing is going to be an upside down parabola. Make sense? It's quadratic. Upside down because the coefficient of p squared is negative. It's going to look like this. Watch my finger. It's going to look like this. If h is 0, you can even say when it's 0. It's 0 when p is 0 or when p is L. Say right there at 0 and right there at, let's pretend that's L. This is what the graph looks like when h is 0. When h is 0. And as h increases away from 0, we're subtracting it. The graph is going to shift downward. Maybe look something about like this. When h is positive and small, and maybe look something like this when h is positive and larger. I'll just say large. When h is positive and large. How large is large? Well, large enough that the graph is always below the axis. How could you figure out what value of h would make it go below the axis? You could figure out the value of h that makes it just touch the axis. If you use the quadratic formula, I won't do that, but if you want a challenge problem, you could figure out what value of h will make it just touch the axis. The answer is going to depend on k and L. When h is bigger than that, it's going to go below the axis. Why is that important? Why is that relevant? We are interested in the differential equation and the slope field and solutions. You can use these graphs to draw the slope field and the solutions. That's the point. Like I showed you last Friday, make another graph. Now put t on the horizontal axis and the dependent variable for the differential equation, in this case p, on the vertical axis. Don't let it bother you that p is horizontal there and vertical there. It's not a big deal. Just get over that conceptual weirdness. just something to get used to, okay? It's a worthwhile thing to draw both graphs in the way that we're doing. In the case where H is 0, case H equals 0, what do solutions look like? The fact that the right-hand side graph is 0 when P is 0 or L means you've got equilibrium solutions at 0 and L. Why? Because if the population happens to equal L, the carrying capacity, this right-hand side, when you plug in P equals L, is 0. The second coordinate at that point right there is 0. But that second coordinate represents a derivative of a solution. The derivative of the solution is 0. And it's always 0 along that line. That horizontal line's got to be a solution, an equilibrium solution of the differential equation. Same at P equals 0. And it makes intuitive sense too. There's no fish. There will continue to be no fish. You don't allow fish to be brought in, okay? Right? Of course, in real life, people do stock lakes, but we're not allowing that, right? Because we want to keep the models simple. If there's no walleye to begin with, there's going to be no wildlife for all time. And on the other hand, if the population is up at the carrying capacity, maybe 10 million walleye, well, yes, it technically does go up and down as fish die and are born. But effectively, the death rate and birth rate are equal. And so in real life, the population at least stays approximately constant. Yes, real life's more complicated, but we say it's approximately constant. That doesn't mean we know necessarily what the carrying capacity is, by the way. Just because there is a carrying capacity, a hypothesized carrying capacity, doesn't mean you know what it is. I don't know what the carrying capacity for walleye and Lake Mille Lacs is. To even call it a particular number might be a little bit of a oversimplification. I'm sure it is. But again, in mathematical modeling, you have to simplify things, because if you try to make it too accurate, then it just becomes too complicated. What do other solutions look like? When P is between 0 and L, the population is growing. This function has positive output. dp dt, slopes of solutions are positive. In fact, they're maximized at L over 2. And these other graphs should be maximized there as well, but I didn't draw that. They're maximized at L over 2. Pretend the drawing is better than it is. There's L over 2. That means in the slope field, when P is L over 2 along this horizontal line right about there, the slope marks have the highest possible positive slope. Solutions, when they cross that line, in fact, are going to have inflection points where the graph changes from concave up to concave down, because that's where the slope is highest. And all solutions are horizontal translations of each other for an autonomous equation like this. Yes, the slope marks have slopes close to 0 when you're close to 0 or L, because the output of the function here is close to 0 when P is close to 0 or L. And the slope marks are going to have negative slope when P is negative and gets steeper and steeper as P becomes more negative. And negative up here too. And the other solutions are going to look like this. The ones that are down here where P is negative have no relevance for fish. But mathematically, they're still solutions. The ones that are up here do have relevance for fish. If the population is higher than the carrying capacity because somebody did stock the lake or something too full, then they're going to die off faster than they're born. the overall population is going to go down. What would happen to this picture as H, the harvesting rate, increases? Because this graph goes down here, that means its p-intercepts get closer and closer together. That means these equilibrium solutions get closer and closer together. And in fact, once H gets large enough, so this graph goes below the axis, there's no equilibrium solutions at all. And dP/dt is always negative. Solutions are always going down. The fish die off, no matter what the initial population is. So the practical consequence of this is figuring out what is that harvesting level that would lead to a fish dying off, no matter what the initial population is. And because the model's not perfect, stay far away from it. Stay far away from that harvesting level that would lead to all the fish dying off, no matter what the initial population is. Do people really do this kind of thing? To some degree, but they when they do it, they are aware it's an oversimplification. But you'll see people write papers related to this kind of stuff. Yes, it's not perfect. Can Mathematica solve it when there's harvesting? I was surprised by this when I initially tried it. It actually can. If I put a minus h in here, right there, can actually solve it. It's not very pleasant looking. Make it a tiny bit more pleasant looking by doing / expand. Yeah, not much more pleasant looking. Tangents and arctangents, are you kidding me? Lots of square roots, even a 3/2 power. Does it work? I think so. So it can even handle it with harvesting. If you try to up the level of accuracy by making the harvesting not constant, but maybe a sinusoidal function, even just a plain old sine of t, though that would, it's not quite the best thing to do because that would make the harvesting negative sometimes. All of a sudden it doesn't work. Thinking, and it never comes up with an answer. Why? It's just too hard, that's why. Nobody can do it. However, people can still think about the slope field and they can still draw solutions. You can still think about it qualitatively. It's not autonomous though anymore. So graphing, you can't really graph the right-hand side function anymore. You can't do this kind of thing anymore. You can still graph the slope field, though, and you can still approximate solutions. Okay, so this is the content of section 11.7. If you do the reading carefully in 11.7, if you haven't done it, you should do it. You will see reading related to what I've been saying, and it should help you understand better. The only thing that I do differently than the book is the phi notation and doing the generic IVP kind of stuff. They don't do that quite as much. Maybe they do it a little bit, but not quite as much.